We will now solve problems using the concepts of specific heat and latent heat. Now remember the major difference between specific heat and latent heat. For specific heat, a change in temperature is involved. For latent heat, there is no change in temperature involved. So during a temperature change, the quantity of heat absorbed or liberated is mass multiplied by specific heat multiplied by the change in temperature. On the other hand, the amount of heat absorbed or liberated during a change of state is mass multiplied by either latent heat of fusion or latent heat of vaporization. Alright, let's start with example 1. A solar home contains 10 to the power 5 kilogram of concrete of specific heat capacity 1 kilojoules per kilogram per Kelvin. 1000 joules per kilogram per Kelvin. How much heat is given off by the concrete when it cools from 25 degrees to 20 degrees Celsius? Now here we need to find the quantity of heat given off when the temperature changes. So it involves only specific heat. Alright, let's pick the data. Mass of the concrete is 10 to the power 5 kilogram. The specific heat of that substance is 1000 joules per kilogram per Kelvin. The change in temperature delta theta is 25 minus 20 is 5 Kelvin. Now remember, the temperature interval 5 degrees Celsius is the same as 5 Kelvin. Although their starting points are different, the intervals are the same in Celsius and Kelvin. Okay. The quantity of heat absorbed in order to achieve this is, in order to achieve a change in temperature, is mass times specific heat times change in temperature. We know all those values. Mass times specific heat times change in temperature, and that is 5 times 10 to the power of 8 joules. In fact, there are cold regions in the world where substances of very high specific heat are heated during the time electricity is very sparsely used. You know that there are peak times for electricity and there are dull times. So in England, you can actually buy electricity cheaper at certain time. That means if you use that cheaper electricity to heat substances that have very high specific heat, and you are storing that heat during the evening hours when the electricity is very costly, you can turn off, and the heat that you stored during the day will now heat your home. You see, that object that has increased its temperature will now throw away heat, will actually warm up your house. A very economical way of heating homes. Alright, let's look at a principle of calorimetry, a very important principle in doing heat calculations. Now what is calorimetry? Calorimetry is the science of calculating amount of heat lost or heat gained, heat absorbed, heat liberated, and so on. Now when hot objects are mixed with cold objects in a thermally insulated container, the hot objects will lose heat and cold objects will gain heat. Is that right? And if the system is insulated from the surroundings, we can make a conclusion. When thermal equilibrium is reached, we can say that the total heat lost by the hot objects will be equal to the total heat gained by the cold objects. We assume here that no energy is either given out or gained from the surroundings. You see, heat exchange takes place in a thermally insulated environment. When that happens, the amount of heat lost by hot objects will be equal to the amount of heat gained by the cold objects. If you practice this, you can solve any problem in calorimetry. As long as you know how to calculate the amount of heat lost or gained. The amount of heat lost or gained when there is a change in temperature is mass times specific heat times change in temperature. On the other hand, the amount of heat gained or lost during a change of state without a change in temperature will be mass times latent heat. All right. Now this principle can be used to solve for unknown quantities. And this insulated container that we use in the lab, if you come to the campus to do a lab in this kind of subjects, we will be using this thermally insulated container to perform the experiment. And such a container is called a calorimeter. A calorimeter. Now here is a typical example of a calorimeter. A calorimeter has a housing. This is the housing. And inside, this is where we allow heat exchanges to take place. This is the isolated or insulated container. You can see there's an insulator there which will insulate this from the surroundings. And you use a lid like this, and you use, this is called a stirrer that can be used to stir. So this is part of the calorimeter, and in order to measure temperature you can insert a thermometer through this hole. So this is a thermally insulated container, and this is called a calorimeter. And most of the experiments that we do in the lab on heat exchangers are done in a calorimeter. All right, let's do a problem. Example 2. How much heat must be removed when 100 grams of steam at 150 degrees Celsius is cooled and frozen into 100 grams of ice at 0 degrees Celsius? Well, we have actually done a similar problem, and let's set it up in a similar way. What are the given quantities? Where do we start here? Mass is 0.1 kilogram, that is 100 grams of steam. So we start with 100 grams of steam at 150 degrees Celsius. Tell me, what will happen to that? You're going to remove heat from there. So this steam at 150 degrees Celsius will first cool down to 100 degrees Celsius. There is a change of state. Now you are given specific heat of steam is 2.01 kilojoules per kilogram per Kelvin. We can find the quantity of heat liberated during that time. So specific heat of steam is 2.01 kilojoules, 2010 joules per kilogram per Kelvin. Steam at 150 degrees Celsius cools to steam at 100 degrees Celsius. The temperature of steam falls, changes. That means the amount of heat liberated during that time will be, what is the amount of heat liberated? Q1 equal to mass times specific heat of steam times the change in temperature. Mass is 0.1 kilogram. Specific heat is 2010 joules per kilogram per Kelvin. The change in temperature, you can see I wrote here negative 50 Kelvin. We don't need that negative. Well, the negative tells you that the heat is liberated. As long as you know that and keep that in mind, you don't need to use the negative sign. So I use the positive sign. This is the amount of heat liberated when steam at 150 degrees cools down to 100 degrees Celsius. And that will be 1.01 times 10 to the 4 joules. And if we do that on a graph, we start here at 150 degrees Celsius. The steam cools down to 100 degrees Celsius, losing this much amount of heat, 1.01 times 10 to the power 4 joules. Alright, now steam is at 100 degrees Celsius. What is going to happen to it? It is now going to change its state from steam to water. So all the steam at 100 degrees Celsius is now going to condense back to water at the same temperature, a change of state. What is the quantity of heat liberated during that time? Steam at 100 degrees Celsius changes to water at the same temperature. The amount of heat liberated is mass times latent heat of vaporization. There is no change in temperature there. It's a change of state. Now that will be mass is 0.1 kilogram, latent heat of vaporization of water. I have not given it to you here. All those are standard values. You must be able to use it from the table that I have provided. That will be 2.26 times 10 to the 6 joules per kilogram. And that is 2.26 times 10 to the 5 joules. How is that going to be represented here? Here, all the substance is steam. Steam at 100 degrees Celsius is going to change to water at the same temperature. See that? There is no change in temperature. And the amount of heat lost is 2.26 times 10 to the 5 joules during that time. Alright, what's the next step? Water at 100 degrees Celsius is going to now lose heat, cool down to 0 degrees Celsius. Alright, water at 100 degrees Celsius cools down to water at 0 degrees Celsius. What is the amount of heat lost during that time? There is a change in temperature. Therefore, the amount of heat lost during that time will be mass times specific heat times the change in temperature. mc delta theta. Mass is 0.1 kilogram. Specific heat of water is 4180 joules per kilogram per Kelvin. And the change in temperature from 100 degrees, it falls to 0 degrees. The change in temperature is 100 Kelvin. So the amount of heat lost during that state is 4.18 times 10 to the 4 joules. How will we represent it here? Water at 100 degrees here is going to cool down to 0 degrees Celsius. This is the state, and the amount of heat lost during that time is 4.18 times 10 to the 4 joules. Okay, what is the next stage? Water at 0 degrees Celsius is going to freeze to ice at 0 degrees Celsius. No change in temperature. It's a change of state. The amount of heat liberated during that time is mass times latent heat of fusion. So water at 0 degrees freezes to ice at 0 degrees, liberating a quantity of heat Q4 is mass times latent heat of fusion. That is 0.1 kilogram times 3.34 times 10 to the 5 joules per kilogram. And that is 3.34 times 10 to the 4 joules, represented by this ice, water at 0 degrees now become ice at 0 degrees. You can see the quantity of heat now given out. We started with steam at 150 degrees Celsius. It cooled down to 100 degrees Celsius, losing an amount of heat mc delta theta. Steam at 100 degrees Celsius condensed water at the same temperature, no change in temperature, a change of state, losing an amount of heat mass times latent heat of vaporization. Water at 100 degrees cooled down to 0 degrees, losing an amount of heat mass times specific heat times change in temperature. And finally, water at 0 degrees froze to become ice at 0 degrees, losing an amount of heat mass times latent heat of fusion. So the total amount of heat liberated is the sum of all these. If you add all that, can you check it? Is this right? 3.113 times 10 to the 5 joules. I have told you, when I do any problem, always be ready with your calculator and check all the calculations. Alright, so be actively involved in learning. And that is one way you will not sleep, because my voice sometimes put people to sleep. Okay. Alright, next problem, example 3. Can you read that problem? If 500 grams of molten lead at 327 degrees Celsius is poured into a cavity in a large block of ice at 0 degrees Celsius, how much of the ice melts? Can you visualize what happens here? We have a molten lead at 327 degrees Celsius. That is the melting point of lead. So what is going to happen to that molten lead when it is poured into a cavity of ice? First of all, liquid lead at 327 degrees Celsius will become solid lead at the same temperature, liberating an amount of heat mass times latent heat of fusion. Is that right? Latent heat of fusion of lead. And I think I've given it to you. LF, latent heat of fusion of lead, is this. And then lead, the solid lead at 327 degrees Celsius will lose its temperature to what temperature? To 0 degrees Celsius, the temperature of ice, liberating an amount of heat mass times specific heat of lead, that is given here, times the change in temperature. The change in temperature is 327 minus 0. So you can see the total amount of heat lost by lead. Now where is all that heat going? All that heat lost by lead is now absorbed by some amount of ice to melt. So what all ice is doing is changing its state from solid to liquid. Is the temperature of ice changing? No. So if m kilograms of ice gets melted, the amount of heat absorbed will be m times latent heat of fusion of ice. You see? And you can now equate the two. The amount of heat lost by lead equal to the amount of heat gained by ice. Let's do that. Molten lead becomes solid lead at 327 degrees Celsius and then cools down to 0 degrees Celsius, giving up its heat. Then m kilograms of ice melts by absorbing all that heat given up by lead. Alright, let's start by looking at each stage. Stage 1, molten lead at 327 degrees Celsius becomes solid lead at 327 what is the amount of heat liberated? Q1 equal to mass times latent heat of fusion. Is that right? A change of state without a change of temperature. That is, mass is 0.5 kilogram, 500 gram, and the latent heat of fusion of lead is given as 2.47 times 10 to the 4, and that will be 1.235 times 10 to the 4 joules is given out during that state. And on the diagram it is this. So all the lead is liquid on the right side and all the lead is solid on the left side, and the amount of heat given out is 1.235 times 10 to the 4 joules. What is the next stage? Lead at 327 cools down to 0 degrees Celsius. What is the amount of heat liberated during that state? There is a change in temperature. The amount of heat liberated is mass times specific heat of lead times the change in temperature, mc delta theta. Mass of lead is 0.5 kilogram. Specific heat of lead is given as 130 joules per kilogram per Kelvin, and the change in temperature is 327 minus 0, that is 327 Kelvin. Let me remind you one more time. The temperature interval 327 degrees Celsius minus 0 degrees Celsius is 327 Kelvin. The temperature intervals in degrees Celsius and Kelvin are the same. And this will be 2.126 times 10 to the power 4 joules. Now, this is the stage when that much of energy is lost by lead. Now, what is the total heat lost by lead? Is Q1 plus Q2, that is 3.361 times 10 to the 4 joules. And now, all this heat loss is going to be absorbed by ice. Let's set up the equation for the heat absorbed by ice. Now, m kilograms, suppose m kilograms of ice melted using that heat. M kilogram of ice melts by absorbing all the heat given up by lead. Heat absorbed by m kilogram of ice to melt without changing its temperature is mass times latent heat of fusion. And that will be m kilogram times latent heat of fusion of ice is 3.34 times 10 to the power 5 joules per kilogram. And we will write it as 3.34 times 10 to the power 5 m. We need to find the value of m. So many joules. So don't confuse here. This is this many numbers times m. We need to find that m. Now, how do you find that m? This amount of heat absorbed by ice equal to this amount of heat liberated by lead. So we will equate the two. And this is the amount of heat absorbed by ice. I use the blue line for that. Now, heat lost by lead equal to heat absorbed by ice. Therefore, 3.361 times 10 to the 4 joules is the heat lost by lead, and that's equal to 3.34 times 10 to the 5 m joules that is absorbed by ice. Can you solve for m from here? M will be this number divided by this number, and that's equal to 0.1 kilogram. Only 100 gram of ice melts by using all that energy. Why is the amount so low? Because the latent heat of fusion of ice is a very large quantity. And that's the reason why on the surface of the earth there are large quantities of water in the frozen form. But you know, the global warming is actually doing a lot of damage to those ice peaks. Is that right? They are melting at a much faster rate. All right, so we must take care to preserve our environment. Okay, let's do another problem. A well-insulated bucket contains 150 grams of ice at 0 degrees Celsius. If 20 grams of steam at 100 degrees Celsius is injected into the bucket, what is the final equilibrium temperature of the system? Is any ice left afterward? You see, you need to understand, visualize the problem if you want to do it. What is happening here? We have 20 grams of steam at 100 degrees Celsius is injected into a bucket. What is the final equilibrium temperature of the system? Now, what is contained in the bucket? A well-insulated bucket contains 150 grams of ice at 0 degrees Celsius. So it is into this ice that you inject the steam. Now, can you tell me what are the processes that happen there? Well, first of all, steam at 100 degrees Celsius is going to condense to water at the same temperature, releasing an amount of energy. Then, water at 100 degrees Celsius is going to come down to a lower temperature. We don't know what that lower temperature is. We are supposed to find that lower temperature. Now, if the lower temperature is 0, that means there is still some ice left there. If all the ice melted, then after melting, the water will increase its temperature to this equilibrium temperature. So we will assume that all the ice has melted, and the melted ice now increased its temperature to that equilibrium temperature. Okay, let's start by talking about it. Steam at 100 degrees Celsius condenses to water, releasing a quantity of heat. What is the quantity of heat released by steam at 100 degrees Celsius when it condenses to water at the same temperature? Q1 equal to mass times latent heat of, what's the mistake I have here? Vaporization, not LF, because steam is condensing to water. It must be L sub V. I'm not making the correction here, you need to make that correction. Q1 equal to mass times L sub V. That will be 0.02 20 grams of steam, 0.02 kilogram times, I have used the right value for L sub V here. Although I wrote LF here, I have used the value of L sub V here. That is 2.26 times 10 to the 6, and that is 4.52 times 10 to the 4. Let's do it on a graph. Where will that look on the graph? We have steam at 100 degrees Celsius here is all that steam condensed to water at the same temperature here. So the amount of heat liberated is 4.52 times 10 to the 4 joules. And now, let's assume that theta is the equilibrium temperature. That means somewhere above 0. Let that be here. Let this be theta. We don't know what value it is. That means this water at 100 degrees Celsius here is going to cool down to that equilibrium temperature. Right? So, if theta is the equilibrium temperature, this water at 100 degrees Celsius cools down to theta degrees Celsius here, releasing an amount of heat. See, this time there is a change in temperature. What is the amount of heat released? Mass times specific heat of water times the change in temperature. Well, mass is 20 gram, that is 0.02 kilogram. Specific heat of water is, what is it? 4,180 joules per kilogram per Kelvin. What is the change in temperature here? The temperature is changed from 100 degrees Celsius to theta, so that will be 100 minus theta. So that will be mass times specific heat times the change in temperature is 100 minus theta, and I calculated that as 0.02 times 4,180 is 83.6 times 100 minus theta. That is the change in temperature during that stage. There you are. It's from here to here. That is 83.6 times 100 minus theta. And now, we have now reached the equilibrium position from this side. Let's now start from the ice side. Well, if the equilibrium temperature is greater than 0, we then assume that all the ice has melted. Is that right? Let ice at 0 degrees Celsius melts to become water at 0 degrees Celsius. That is the first stage. All the ice first has to melt. So ice at 0 degrees Celsius melts to become water at 0 degrees Celsius. What is the quantity of heat absorbed during that time? It will be Q3 equal to mass of ice times the latent heat of fusion of ice. Now, mass of ice is 150 gram, which is 0.15 kilogram, times latent heat of fusion is 3.34 times 10 to the 5. That is 5.01 times 10 to the 4 joules. Now, that will be represented over here. All the ice at 0 degrees has now become, water at 0 degrees. Ice has changed to water by absorbing this much amount of heat. And now, this water needs to go up to the equilibrium temperature so that both meet at the same temperature. This water at 0 degrees heats up to theta degrees Celsius. What is the amount of heat absorbed during that time? Can you do that on your own? Q4 is mass times specific heat of water times the change in temperature. What is the change in temperature during this time? It will be theta minus 0. From 0 it increases to theta. It will be theta minus 0. So mass is 0.15. Specific heat of water is 4,180 joules per kilogram per Kelvin. The change in temperature is theta minus 0, which is theta itself. So I can multiply these two numbers and then multiply by theta. It gives me 627 theta is the heat absorbed during that time. Water increases from 0 degrees to theta. There you are, 627 theta. Now, if you look here, the green lines represent the amount of heat liberated, and the red lines represent the amount of heat absorbed. The total heat liberated must be equal to the total heat absorbed. Alright, let's do that in the next page. Total heat lost by steam is this quantity plus this quantity. There you are. And the total heat absorbed by ice is this quantity plus 627 theta. There you are. And these two quantities must be equal to each other. Heat lost equal to heat absorbed. That means 4.52 times 10 to the 4 plus 83.6 times 100 minus theta, that quantity, equal to 5.01 times 10 to the 4 plus 627 theta. Well, this is now a simple equation in theta. You should be able to solve for theta on your own. I have done that anyway. Distribute these numbers. I produced that. So the only change in this step is 83.6 times 100 minus 83.6 theta. And now leave the numbers on this side and take the theta values on, well, theta values on one side. What does that give you? 627 theta is on the right side. Move that negative 83.6 theta to the right side. The right side becomes 83.6 theta plus 627 theta. And move all the numbers to the left side, and that's what you get. And now simplify that. You get 3,460 equal to 710.6 theta, and therefore theta equal to 4.87 degrees Celsius. Well, because you got a value for theta as greater than 0, you can say all the ice has melted. If all the ice has not melted, you would have gotten a negative value for theta. And if you had a negative value for theta, your conclusion is not all ice has melted. The method of the problem will remain the same. Alright? This is a very important type of problem. I want you to practice this one more time on your own. Alright, let's do another problem. A calorimeter of negligible mass contains 1 kilogram of water at 303 Kelvin and 50 grams of ice at 273 Kelvin. Find the final temperature, uppercase T. We just use uppercase T as the final temperature. A calorimeter, you know what a calorimeter is? Of negligible mass means the heat absorbed by the calorimeter can be neglected. You need only look at the heat absorbed or liberated by its content. That is the meaning that the calorimeter has a negligible mass. Alright, what happens? Ice at 273 Kelvin first melts to become water at 273 Kelvin. The temperatures are given in Kelvin here. You see that? So ice at 273 Kelvin first has to melt to become water at the same temperature, absorbing a quantity of heat. What is the quantity of heat absorbed during that time? Will be mass times latent heat of fusion. Q1 is mass times latent heat of fusion. That will be, what is the mass of ice? Mass of ice is 50 gram. That will be 0.05 kilogram times latent heat of fusion is 3.34 times 10 to the 5 joules per kilogram per Kelvin. Now you see I haven't written any units for the quantities. Alright, you must know that this is in kilogram, this is in joules per kilogram per Kelvin. And that gives you 1.67 times 10 to the 4 joules is the amount of heat absorbed by ice. Let's do that on the diagram. Ice at 273 Kelvin melts to become water at the same temperature, absorbing this much of heat, 1.67 times 10 to the 4. And now what happens? Let us say, what are we supposed to find? Find the final temperature, uppercase T. So let us say that the uppercase T is somewhere here. That means this water at 273 Kelvin will now rise its temperature to this T Kelvin. So water at 273 Kelvin warms to become water at T Kelvin. What is the amount of heat absorbed during that time? Well, there is a change in temperature. Therefore, the amount of heat absorbed will be mass times specific heat times change in temperature. That will be Q2 is mass times specific heat of water times the change in temperature. 0.05, that is the mass of ice that is melted to become now water. Specific heat of water times the change in temperature. You see, initial temperature is 273. The final equilibrium temperature is this T. The change in temperature is T minus 273. Now that will be, multiply these two numbers, that will be 209 times T minus 273. And that is this quantity here. The amount of heat absorbed by water at 273 Kelvin to become water at T Kelvin is 209 times T minus 273. Alright, now we have 1 kilogram of water at 303 Kelvin. You see, the bucket contains hot water. Its temperature is 303 Kelvin. Now, it is now going to lose heat. From 303, it is going to come down to this T. Is that right? Alright, let's do that. The total heat absorbed by ice will be this quantity plus this quantity. There you are. And that will be, I just distributed these in here. That gave me 209 T minus 40,357. I just distributed this and added the numbers, and this is the result. And now water loses heat in cooling down from 303 Kelvin to T Kelvin. What is the heat lost by that water? The heat lost by water is mass times specific heat of water times the change in temperature. What is the mass of that water? 1 kilogram. The amount of hot water in the bucket is 1 kilogram times specific heat of water is 4,180 times the change in temperature. The change in temperature is from 303 to T. So that will be 303 minus T. And I distributed that and I got this big number minus 4,180 T. And now what do? The total amount of heat absorbed equal to the total amount of heat lost. Well, this is the amount of heat lost by the hot water. The total heat absorbed equal to total heat lost. That means this quantity equal to this quantity. What all you need to do is combine terms containing T, move this to the left and move this number to the right. We get 4,389 T equal to this big number. Well, that would be 1,306,897. Therefore, T equal to, divide the right side by this number, you get 297.8 Kelvin, and that is the final equilibrium temperature. Again, a very, very interesting type of problem, and you must be familiar with these kind of problems. Now, I think I have done a number of representative problems. I'm going to stop the lesson here. I have recorded this lesson as 2 parts. Remember, in the text, it is given as 1 lesson. Also in the PowerPoint, it appears as 1 lesson. But for the convenience of presenting it on lectures, I have divided it into 2.1a and 2.1b. So do the homeworks and get back to me if you need any assistance. I will see you for next lesson later on.